You ever stop and think about that tiny little brain living in your pocket? We're going to pull back the curtain on the one piece of tech that powers pretty much everything in our modern world. It's not magic, but honestly, it gets pretty darn close.
I mean, really think about it for a second. How does that slab of glass and metal you're holding know how to do, well, everything? How does it instantly pull up a map, play a movie, and connect you with someone on the other side of the planet? The answer is both way simpler and way more complicated than you might think.
And this is it. This is the answer. It's called a microprocessor. And yeah, at first glance, it just looks like this incredibly intricate work of art, right? Like a sprawling city map with millions of tiny roads and buildings, all packed onto a sliver of silicon smaller than your pinky nail.
Okay, so what is it in plain English? Well, a microprocessor is basically a tiny programmable chip. It takes in data, just a stream of ones and zeros, and then it follows a list of instructions to process that data and give you a useful output. So when you tap an icon on your screen, that's the input. The app opening up, that's the output. Simple idea, but the execution is just mind-blowing.
To really wrap our heads around how this all works, let's think of it like this. Imagine our microprocessor is a world-class chef. But this chef works in a tiny, super high-tech kitchen at an impossible speed. Their only job is to follow recipes and crank out dishes, but they do it millions, even billions of times every single second.
So here's a look at the floor plan of our kitchen. See how it's broken up into different sections? Just like in a real restaurant kitchen, every single part has a very specific job to do, and they all have to work together perfectly to get the meal, or in our case, the calculation, done on time.
All right, let's meet the crew. The control unit, that's the chef's brain. It reads the recipe. The ALU, that's all the tools, the ovens, the knives. It does all the actual chopping and cooking. The registers, think of that as the cutting board, holding whatever ingredients the chef is working with right now. The memory is the giant walk-in pantry, storing everything. And maybe most importantly, you've got the system bus. He's the kitchen runner, the guy who has to carry everything back and forth between the pantry and the chef. A perfectly oiled machine.
Or is it? You see, there's a huge problem in our kitchen. Our super-fast chef has hit a major snag. It's a massive, system-clogging traffic jam that can bring the entire operation to a screeching halt.
And this right here illustrates one of the most famous problems in all of computing. It's called the von Neumann bottleneck. See, our chef, the CPU, is unbelievably fast. The pantry, our memory, can hold tons of stuff. But there's only one narrow little hallway, the bus, connecting them. This means our poor kitchen runner can only carry one thing at a time. He can go get a recipe instruction or he can go get an ingredient. He simply cannot do both at once.
Now let's see what that actually looks like in the real world. This chart is, well, it's kind of shocking. That tiny little bar on the left, that's the time our chef spends actually cooking, just over 5 milliseconds. But that giant bar on the right, that's the time spent just waiting for the runner to bring the next ingredient. Over 300 milliseconds. This isn't just theory. It's why your super powerful computer can still sometimes feel slow. The chef spends almost all of their time just standing around, waiting for a delivery.
So what's the bottom line? In that specific task, the processor, the most powerful part of the entire system, is only being used, wait for it, 1.67% of the time. That's it. For over 98% of its life, it's just idle, tapping its foot, waiting for data to arrive. It's a ridiculously inefficient system.
So obviously, computer engineers weren't just going to accept that, right? They looked at this situation and said, nope, we can do better. So they started designing smarter kitchens to help the chef cook faster and finally beat this crazy bottleneck.
One of the first solutions was a totally new kitchen layout. So on the left, you've got our original design, but on the right is something called the Harvard architecture. And the idea is just brilliant in its simplicity. They thought, what if we just build a second hallway and hire a second runner? Now, one runner can fetch recipes while the other fetches ingredients, getting them to the chef at the same time. It's a game changer. The next big idea was something called a cache. Sticking with our analogy, instead of making the runner go all the way down that long hall to the pantry for every single thing, what if the chef had a little mini fridge right next to him? And what if that mini fridge was always stocked with the most common ingredients? You know, salt, pepper, oil, onions. That mini fridge, that's the cache.
And of course, engineers didn't just stop at one mini fridge. They built a whole hierarchy. The L1 cache is the fastest. Think of it like the spice rack right on the counter, instantly within reach. The L2 cache is that mini fridge, just a step away. The L3 is a bigger, secondary fridge in the back room. And only if the chef can't find the ingredient in any of those places does the runner have to make that long, slow trip to the main pantry, which we call RAM.
Okay, so beyond the kitchen layout, there are also different cooking philosophies. One is called CISC. That's like a recipe that just has one complex step. Make lasagna. The other is RISC. That breaks it down into tons of simple, fast steps. Boil noodles, brown meat, layer cheese. And while traditional PCs often use that complex CISC approach, your phone and other devices use the simpler, more energy-efficient RISC method.
Now, all of these really clever designs, the extra hallways, the mini fridges, all of it, they get supercharged by one other absolutely relentless force in technology, making every single part of the kitchen smaller and smaller and smaller, year after year after year. This incredible graph shows a trend called Moore's Law. It's basically the observation that the number of components we can cram onto a chip doubles about every 2 years. Just look at that steep downward curve. It represents one of the most powerful and consistent forces in all of human technology. It's the engine of the modern world. So what has all that shrinking gotten us? It means that today we can fit billions, with a B, of tiny switches called transistors onto a single chip. And the components we're building with now, they are literally smaller than a virus. Just let that sink in for a second. It is absolutely staggering.
This timeline really puts the sheer speed of that progress into perspective. In 1971, a single component was 10 micrometers wide. Fast forward to the year 2000, and it was 180 nanometers. That's over 50 times smaller. And by 2020, we hit 5 nanometers. That's a scale so small our brains can't even really comprehend it.
And that leads us to the final and most important question. We have perfected our kitchen designs, and we have shrunk our tools all the way down to the very edge of what physics will allow. We are now literally building things at the atomic scale. So, as we slam into these fundamental physical limits, what does the next evolution of the microprocessor, that brain in all our pockets, even look like?